Okay, guys. I won't lock anyone up just yet. Okay, guys, let's get going. Um, Sorry for the minor delay there. It's not like I'm late, really, but I feel bad because I was like, oh, we're learning about the cytoskeleton, and it's Halloween. There's got to be a good, like a good cartoon or something, and there's not. And so that's what I was doing with my valuable time. Okay, exam 2. Grab them after class. They're right here. You guys rocked it in a major way, which says a lot of things to me. It tells me that often people don't know how to organize their thoughts well enough to study. Because that was the only difference between 1 and 2, right? Is that I sat here and told you guys, well, think of it this way. And that's apparently very valuable because the average was, it went from a 75 last time to an 83 this time. And not only that, look at the number of people who got over 100. That's amazing. It's like 15 people got over 100. Basically, the majority of the class got over an 80. Well, hence the average of being over an 80. Definitely, there are some people who are still struggling, which brings me to my second observation, which my husband told me not to share, but I'm going to anyways. He was like, don't tell them that. And I was like, well, it could be helpful, so we're going to go there. So I was putting in everyone's grades, and I noticed on Blackboard, people get the same grades again and again. Exam 1, 71. Exam 2, 70. Across the board, people get the same grades over and over again. And I was like, that is so weird, right? Totally weird. And so then I looked at the pretest scores, and I was like, I wonder if people are getting the same grades as their pretest. And I plotted it, and I did linear regression and got my R squared, and holy cow, you guys are correlating extremely well with your pretest grades, which is really scary because that means, like, I don't know, that I'm not doing anything. I don't know. But I think what it means, actually, so I did a few quick analyses when I should have been going to sleep. And hence my too much coffee today. And so I did one where I compared your average exam scores with your pretest grade and looked for a correlation. And then I did one where I took your average, like your complete average, and compared them with the pretest. And it's nearly a perfect correlation when you look at pretest versus complete average. Like take, in-class exams plus quizzes plus just everything that you have so far. So percentage of total possible points. And if it's just in-class exams, it doesn't correlate as well, which probably accounts for some people have test anxiety or this and that. That's going to affect things. So if you take that out of the equation and just look at complete average, there's a huge correlation. And so I thought about it, and I was like, well, how can I help these folks? I mean, if you're on the end where you got it, perfect score on your pretest, you're like, well, what do I care? I did really well on the pretest. But if you didn't do so well on the pretest, and you're still not doing so well, it tells me that there's some kind of deficit that started at like 201, and then at 309 you still didn't figure something out, and now here you are at 408 still like lacking some kind of basic concepts. And I think it could help to understand that, because then you can go back and think to yourself, okay, well, what am I not getting? I don't know if there's a way to like figure that out, but maybe going through over winter break, going over your 201 and 309 stuff and thinking about those major concepts of proteins having biochemical properties and interacting with each other and stuff like that. Because I think that if you all got those concepts, you wouldn't have some of the problems you're having now. Now, everyone rocked this exam, which was awesome, but there were certain things that I saw over and over again that really kind of made me realize that there were those kind of deficits in major concepts. Like a lot of people were telling me about domains moving around. They're part of a protein. Like people were like, and then this domain goes away. Or people were telling me about when I asked about receptor phosphorylation, and in that first essay, people were telling me that phosphorylation of the receptor resulted in exposing an NLS on the receptor. So I think it's not that you didn't know that question. It was that there's something about the larger picture of how proteins work and interact with each other and function as little machines that is missing somewhere. So I'm going to try to figure out. So whenever you guys, the way you guys can help me and your classmates is as we're going through these lectures, when there's something that you just don't get, don't sit there in silence feeling embarrassed. Raise your hand and be like, this might be a stupid question, but I know it's not because you say there's no stupid questions. And then ask me, say, what is a protein? Or whatever it is, because I think you're going to help your classmates. Okay, I'm done ranting. Those are my thoughts on exam 2. But overall, you guys rocked it. Recitation is canceled for the week. Boo. Are you all sad? Lucky you. Yeah, there's just no way. I was trying to figure it out, and there's no way to make up Monday, and then that's like a third of the class that doesn't get to take a quiz, and they're not going to get credit for it, and it just makes it all not equal. So that's that. Okay. So here are a few more reasons to care about the cytoskeleton. Let me lock the door. Let me lock everyone out. Okay. As if you don't need more reasons to care about the cytoskeleton. Let's see. Okay, so the little red dots are vesicles. And the green are microtubules. And there's a lady with, let's go back and do it again. I love it. You see them moving around? Remember we learned about vesicular transport and vesicles taking things to places, and look at those vesicles moving. That's completely dependent upon the cytoskeleton, right? Do you see them moving? Should we do it once more? Do you want to see the lady in the sports bra? Isn't that cool? Look at them moving around. That's really happening. Who loves it? Do you guys care? Are you guys glad you're here? Okay. Oh, where were we? Okay. And then another one. This is actin and tubulin during mitosis. And so you're not going to see your DNA, just actin and tubulin. Okay, so let's see. Actin, we're going to see. Actin is red, and MAP4, which is a tubulin binding protein, is green. Let's do it again. So you can see a few things. You see the edge is red, right? So your actin is your, whoa. Let's do it again, because that was really fun. See, the border of your cell is red, so actin's often involved in that movement of the cell. And then also notice you're seeing your mitotic spindle forming. And you're also seeing some red between, once more. You're also seeing some red when the cells divide. There's 2 cells there. It's not just one. And they're both going through mitosis at the same time, kind of. And you can see there's a line. One more thing. Yeah.
Can you put it one time but stop that one?
No, you don't get to see the video. Sure. Here, I wanted to show one thing. Okay, look at that. See, there's your mitotic spindle. And then right between where the cells are splitting, you're going to see some red of actin. That's your contractile ring. See if you see it. There you go. Very cool. Did that help? Okay. Okay. You guys want to just watch videos all day? Okay, I wish we could, but some of us say I'm not doing it. Okay. What else should we talk about? All right. Okay. So now that you really care and that you understand that the cytoskeleton is not just about providing structure to a cell. I mean, that's important, clearly. Let's learn a little bit more. So this is where we had left off the other day. We were talking about formation of these cytoskeletal filaments, actin and tubulin, from protofilaments. So they start they start as being monomers, and they bind to each other, and they bind in this kind of multiple protofilaments interacting together, and that gives them a lot of strength and stability. And then we spoke for a minute about intermediate filaments, and that really does provide cells with a lot of mechanical strength. So there are these very long monomers that interact in a staggered way, and that kind of gives it a rope-like strength. Quite different from microtubules, which are these teeny tiny, they look more like this, these teeny tiny little subunits. And once you start to think about the function of these different polymers, then it will make more sense, because microtubules, they need to assemble and disassemble quickly because of their function and movement, and we'll see that soon. And intermediate filaments don't assemble, disassemble really much at all. And they really need to be very strong, because they're what's giving that cells that kind of strength, so that they don't break and pop and disassociate from the other cells, and disassociate from, like keeping organs together, stuff like that. Okay. So for you guys to understand, I didn't do this last time I taught it, so I just spent a little bit of time putting this part of the lecture together, because there's kind of a language involved with understanding cytoskeletal dynamics and the cytoskeleton in general. And I want to just go through some of the major terms, and then they'll come up again and again and again, and you'll be like, oh, wait, she did tell us we need to understand that concept or that word or whatever. And hopefully that will help with understanding the content. Okay, so the first one is nucleation, and I saw on the quiz people had a hard time with this one, and I think it's because you don't think about nucleation in this context at all. It's basically creation of a stable starting unit, which then allows for rapid polymer growth. So if you've got, in the case of microtubules, you've got these alpha beta tubulin dimers, and they have to bind to each other to create a minimal kind of starting unit, which allows rapid addition of monomer and growth of the microtubule. But until you create this nucleus, it's a lot of like one binds, one leaves, one binds, one leaves. And then once it's more stable and you reach this certain concentration, which is called the nucleus, then you will be able to grow. And so I have this video, hopefully. Where you have, let's see. Okay, so you just got all these monomers hanging out, and then eventually they hit this point where there's enough of them bound to each other that there's this nucleus, which is shown in blue, and then they all start to add and grow faster and faster and faster. So that's what we talk about. It has nothing to do with the DNA. It has nothing to do with atoms and whatnot. It's a whole other new kind of nucleus you get to learn about. Okay. Oh yeah, and so here it has a little bit about critical concentration and about how it all depends on, well, we'll get to that in a minute. We'll come back to this in a minute. Okay, so let's go back to here. Okay, so that's nucleation. So that's a bunch of these monomers binding together until they have a kind of like a critical mass to be able to grow. Until they reach a critical mass, they're just going to keep, the monomers are going to keep popping off. Okay, and this is really important in understanding cytoskeleton, because we're going to go through all these different proteins that function in in basically getting rid of this nucleation step, and that's how they encourage polymerization of actin or microtubules. Right now, you might be like, "What the hell is she talking about?" Which is cool. We're okay. We're okay right there right now. But just keep these terms in your mind and think about them and try to put them back as we talk about this. Try to put them back in and be like, "Oh, that's what she was talking about." Okay, so then we come to critical concentration, which I always don't want to teach because it looks like there's math involved. But we won't be doing any math, I promise. But some people are really good at looking at equations and understanding concepts, so I put it in here. But it's basically the relationship between free monomer concentration and whether or not your polymer, by polymer I mean monomers bound together, right? The relationship between the free monomer concentration and whether or not your polymer is going to be growing or shrinking. It's all related. So at the critical concentration of monomer, the on and off rates are equal. So if you have all these subunits in a tube, right, they're going to like bind, release. You can kind of imagine it in your head, right? And then eventually create a nucleus and then start to grow. And as that polymer is growing, your concentration of free monomer is decreasing, right? Because it's all becoming part of the polymer. And then you reach the certain concentration where there's not that much monomer left in solution, and then subunits start to come off of the polymer. And so the critical concentration is when the on and off rates are equal. Okay, so your concentration, well, I guess you could say your amount of monomers that are bound are dependent upon the concentration of the monomer in solution. So the critical concentration is when on and off are equal. So you can take or leave this concept. I didn't even teach it in the past, but then I found myself having to keep coming back and saying, well, it's all dependent upon how much you have in solution. And then I'm like, well, they never told them critical concentration. So I'm giving it to you and just try to understand that concept. Does anyone need me to talk about it in a different way, or does it make sense? Yes?
What's the 1/k mean?
I don't know. It has something to do with just the fact that that at the critical concentration, on and off are the same, and so it's, I don't know, it was right out of the book. I was hoping the math people would get that part. I know. Are you disappointed in my education?
I'm kind of disappointed in thinking I was a math person.
You know what? If anyone can go through, I kind of get the part. The 1/k did throw me off. If anyone can go in the book, it's right out of the textbook, and look at it and come back on Friday and explain the 1/k to the rest of us, you get extra credit points. Okay, so work on that. Math people, I'm giving it to you. But it makes sense, right? So if you've got, say you're a scientist studying actin polymerization, and so you put a whole bunch of monomer in your tube. There's your tube, whole bunch of monomer, right? And so eventually, some are gonna form this nucleus, right? And so then you're gonna have growth, and you'll have less monomer, and then you'll get to a point though where you're at so that's the other thing is, so they're going to have growth coming in one end and then some coming off in another end, and then eventually you'll get to this point where the concentration is so low that you start having some coming off, so your polymer is smaller, and then you again have a lot more monomer, and that's what it basically is about, how your concentration of monomer affects whether or not your polymer is growing or shrinking. Okay, yes? Yes. Yes. But there are all these proteins, so that is the natural tendency. But what we're going to talk about, why I'm giving you all this basic background, which maybe you, right now you're like, I have nowhere to put this in the box. There's this box and there's all this stuff. There's all these proteins in the cell that function in changing this, in promoting growth or promoting shrinking. And we're going to learn about all these proteins that do that and then how they function in things like mitosis or cell movement and stuff like that. So understanding what's normally happening will help you when I say this bypasses the nucleation step, allowing for more growth, or this breaks down the polymer, which results in catastrophe and stuff like that. And then you'll start to understand it. But this is a good starting place. Okay. Are we good? Are we crying yet? Does anyone want to cry? It's all right. It's all right. I had that conversation with my daughter yesterday. I let her watch this music video that was really sad, and she started crying. She's like not even 5. And she was like, I don't want to watch it. It's so sad. And I was like, but it's okay to be sad, and that means they did a good job because it made you cry. And it was like stop motion animation. So, anyways, it's all right to cry about the cytoskeleton. Okay, so let's keep going with the language. So we've got plus and minus ends, which means that actin and tubulin polymers, they have 2 ends at which monomers add or leave at different rates. And so I put a little picture in for you guys. Here's your polymer, and here's your minus end, and here's your plus end, and things tend to add more quickly to the plus end. And that's why it's called the plus end. In actin, they tend to call it the barbed end. The barbed end is the plus end, and that has to do with the shape of actin. But plus end, that's where they tend to add. Minus end, that's where they tend to leave. And that brings us to the concept of treadmilling, which we will have a nice video shortly showing treadmilling. And, let's go back actually to the critical concentration. Let's go back. Okay, right, because they were talking about critical concentration here. Okay, right, so you have the steady state where your addition and leaving and coming and going are the same, and that's your critical concentration. And I think they're going to show you what happens when you drop below your critical concentration. Oh, so when you're above your critical concentration, then there's more addition. Is it going to tell you below? When it's below, they should start to come off. Yeah, there you go, coming off and going more into solution. So look at this video, and it should help you guys to conceptualize. Okay, let's go back. Okay, so we got our plus and minus ends because they leave and add at either end. Treadmilling. Okay, treadmilling is when your critical concentration, it's a concept of addition and subtraction so that the whole polymer looks like it's moving. And we're going to see some stuff in a minute to illustrate that. But it's basically when your critical concentration at your minus end is greater than your critical concentration at your plus end. And that results in things leaving quickly from your minus end and adding quickly at your plus end. So the whole thing looks like it's actually moving, like on a treadmill where you're moving but you're not. We'll look at that in a minute. Okay, so then there's dynamic instability. And that's the concept, especially when we're talking about microtubules, that they can grow and rapidly shrink. Dynamic instability is right there in the words. And that is really important concept in just microtubule function in general. And so microtubules are constantly alternating between these 2 states of growth and rapid shrinkage. And it's all dependent upon a GTP bound state of the monomers. And we'll go more into this. This is not all you're going to see of this. Okay. Any questions before I move on? Okay, so, yes?
You said they tend to add to the plus end, and does that mean that they can come off of the plus end?
Yeah, so it depends on the filament. So if you've got microtubules, they're pretty much always adding to the plus end because their minus end is in the microtubule organizing complex. It's in this, so yeah, it's just the plus end, where they're always adding and always leaving. with actin, then you tend to have a greater rate of addition at the plus end and a greater rate of leaving at the minus end. But it doesn't mean that you can't have the opposite happen. And we'll get more into it. Okay, so let's go back to nucleation. So that was the language that you need to learn. And so now we'll get into more detail, and hopefully things will become a little more clear. It's not that difficult, but it's just new concepts. Okay, so nucleation is that first initial step required for filament formation. And it looks kind of like a growth curve, right? Who's in 315? Did you guys see this? And there's actually just bacteria here. Well, here there's no bacteria, right? It's just subunits, right? So here they're doing it, the example is actin. And you've got this lag phase where you've got these subunits just kind of hanging out. They're binding and releasing, because the strength of their interaction isn't very strong. And then they get to this point where they reach this concentration they reach this nucleus is what it's called, where all these subunits are bound and their interaction is pretty strong, and this allows it to go into a growth phase. So you get this rapid growth until you hit a steady state phase, which is where you're at your critical concentration, where you've got addition and subtraction happening at the same time. Okay? So the subunits, they spontaneously assemble and disassemble, but it's really unstable, and they don't stick together until they hit a certain aggregate concentration, which is called the nucleus. Okay, nucleation. Okay, so then the filament will grow and reach its steady state. Okay. So the concept to understand is that if you start with a nucleus, you bypass that lag phase, right? So if we just throw in this nucleus of this preformed monomers bound together, this preformed filament, and then add in monomers, it's just going to grow. And a lot of proteins have this function in the cell. So I have one question down here, but before we talk about that one question, my question for you is, why would actin need to grow? Maybe understanding, like having somewhere to put all this information might help you to think about it. Why would actin need to grow or shrink? Yes. Right. So when you have movement of a cell, right, cells move. The way they move forward is by growing their actin, or it's actually the treadmilling function that helps them to move forward. So that's one way. That's one very nice example. So how do you think, though? So there are these proteins that have this function of bypassing the nucleation step. They purposely allow actin to just start growing. So how do you think this might work? Yes.
Could the protein itself serve as a nucleus?
Mm-hmm. And so it might serve as a nucleus. How might it serve as a nucleus? What would it bind to? What would it do?
Binding to the subunits and letting them grow.
Binding to actin subunits, yep, and letting them grow. And we'll get into this. I just want you guys to start thinking about these. Another thing is, remember we just looked at mitosis, and we had the red outline of the cell for actin, and then as mitosis happened, you see this rapid reorganization of the red into the contractile ring. I was trying to get you guys to see that. Well, that reorganization is going to require disassembly of all the actin that's around the edges of the cell and focusing it into this one spot, which is then going to act differently, form the contractile ring that's going to occur during cytokinesis, right? That's going to mediate cytokinesis, the splitting of the cells. So that's going to require disassembly and rapid reassembly of actin. Okay. Thoughts? Comments? Who has power at home? Oh, I should say, who doesn't have power? You don't have power. Is that one person with no power? Oh. well, one person who's here. Maybe all the people who aren't here don't have power, and their cars don't work. Everyone has electric cars. They can plug them in. Okay. Okay, so here's a question from the quiz. Proteins that stabilize the nucleus, actin or tubulin nucleus, not cellular nucleus. I tried to put that there so you would not go in the wrong way. Increase the rate of polymerization by, what did you guys choose? Okay, so I see some A's and some D's. So it was A. So you're completely bypassing nucleation because this protein is acting as these proteins are acting as a nucleus, and so you're bypassing the rate limiting step. Okay. That was one. Okay, so I'm going to try to disperse the quiz questions appropriately with the right material now. We'll see how it works. Okay, so let's talk. We talked a little bit about actin. Let's talk about microtubules. So they're forming from tubulin subunits, right? I just told you alpha and beta tubulin heterodimers. A heterodimer, two proteins that are different that bind together, right? As opposed to a homodimer. What's a homodimer? Same, thank you. Same proteins that bind together. Okay, so there's the alpha tubulin, beta tubulin, which would look like that, right? Or like that if you're looking at the protein structure. And the key here is beta tubulin binds to GTP and has the ability to hydrolyze GTP. And that's a really important concept to understand because the way these heterodimers assemble in forming their protofilament is they assemble so they're so it's beta to alpha interaction, and then you end up with the GTP hydrolysis in the beta, which is at the top. So GTP does bind. What? I don't know where I wrote that. Okay, we'll get back to that. Okay, so microtubules, they're hollow cylindrical structures. So they're made of these different protofilaments, right? So you've got your monomer, which is actually a dimer, it's heterodimer. That's going to assemble into this protofilament with a plus end and a minus end. Remember we talked about that. And then they're going to assemble together 13 parallel protofilaments are going to assemble together and make the microtubule, and there's actually going to be it's going to be hollow in the middle, and it's made from these alternating alpha beta tubulin subunits, and all the different contacts between the subunits are what make microtubules stiff and strong. And if you think about it, they kind of need to be, because remember we looked at those vesicles trafficking along microtubules. If they're not stiff and strong and they break all the time, are we going to have easy vesicular transport? No. Are we going to be able to separate our chromosomes during mitosis if they're not stiff and strong? Right. Okay, so that's important. So they have a long persistence length, which means that they'll persist for a long period of time, right, before they start breaking apart. They're the stiffest, straightest structural element found in most animal cells. Again, they have the structural polarity. They've got a plus end and a minus end. And actin is similar also in that it also has polarity. So the actin has monomers, and it also assembles head to tail together, except for the only difference is they're monomers. And they have a plus end and a minus end in how they assemble. And they bind, so tubulin binds to GTP and uses GTP in their assembly, GTP hydrolysis. And actin binds to ADP. Okay, so they grow and they shrink depending on the concentration of free monomer in solutions. This is going back to that concept of critical concentration. And so this is a picture right here of microtubules actually growing. So here's your minus end. So these are the 13 protofilaments all bound together. and you have them growing, or this could easily be shrinking, right? So they're actually totally falling backwards. So they're going to come together and be stiff and strong. As GTP hydrolyzes, they're going to want to not bind. So association or dissociation is greater at one end than the other. With microtubules, always the plus end. Well, in general, always the plus end. One end can elongate faster, and the other end could shrink faster than the other. The more dynamic end, so the end that's quickly growing or shrinking, is the plus end. Ooh, I'm hungry. Who's hungry? I should have brought candy. Oh my god. Because it's totally going to rain tonight, and I've got like $50 of Halloween candy sitting on top of my fridge that I've been ignoring for about 3 weeks. Really hard to do that. Oh well. Okay. So cells, they like to couple the unfavorably energetic processes to the spontaneous process of microtubule actin growth shrinkage. So some examples of what I'm talking about is to push or pull an attached load. What kind of attached load might microtubules push or pull? Vesicles or chromosomes. Yep. More actually. Well, yeah. Elongating microtubules can push out membranes. Shrinking microtubules can segregate mitotic chromosomes. Elongating actin filaments can help push out the leading edge of motile cells. So these things I keep on bringing up should help you guys to care a little bit. Okay. I'm not saying that you don't. I'm saying it was hard for me to care about the cytoskeleton, so I can relate. Now I love it. It's awesome. Okay. ATP, GTP. Remember I was saying ATP. What binds ATP? Actin. What binds GTP? Tubulin, right? ATP or GTP hydrolysis occurs when a subunit assembles into a polymer. So you've got your monomer, it binds to the growing polymer, and then you have hydrolysis. And it's that hydrolysis of your NTP, nucleotide triphosphate, right? That reduces the binding affinity and enables it to actually dissociate. You're like, wait a minute, what? So binding, so you need to be GTP bound to bind, and then you'll hydrolyze, and then you'll release. And so that's where you get that dynamic instability. It wants to keep binding and removing. So I might refer to it as the T-bound form when it's ATP bound, or the D-bound form when it's G or ADP bound, right? So your T-bound form is more likely to add to the filament, and your D-bound form is more likely to leave. So if this were your plus end, your T is going to want to bind, and your D is going to want to leave. Okay? Okay, treadmilling. We talked about that. I think I have a video coming up. So this treadmilling is resulting from the net assembly. It might sound like I'm repeating myself, but I really want you guys to understand these concepts. Treadmilling results from a net assembly at the plus end, right? So you're having more binding at the plus end. This would be your plus end. And a net disassembly at the minus end. So your net is your big arrow, right? Big arrow, little arrow. And so that's results in the polymer looking like it's moving. So it's maintaining a constant length, right? Because you have addition at one end and removal at the other end. And you get this net flux of subunits through the polymer. So here, this is right out of the book. You can take a look at it a little bit larger. But so here they did an experiment. Some scientists who published a paper on treadmilling. They did an experiment where they were looking at treadmilling of microtubules, and they added fluorescently labeled tubulin. And so you can see there's these landmarks here. So you start here at time 0, and they took multiple pictures over 98 seconds, and it actually looks as if the whole thing is moving, right? Look, it starts over here, and it ends up kind of over here. And that it's not that the microtubule is moving, it's that treadmilling, that addition. So there's a lot more being added at the plus end. and they're leaving from the minus end. Added more at the plus end, leaving from the minus end, and watch it moving. See? Okay, so here's the video. Oh, maybe I'm gonna have to, let's see what it looks like. Whoa, cool. See? Everyone got it? Do I need to do it again? And it's showing you ATP. See, the ATP bound actin is what's adding, ATP is leaving. Fun. Let's do it once more. I like that one. It's pretty clear, huh? See that treadmilling? Notice your ATP actin is turning into ADP actin because you're hydrolyzing your ATP. See? Okay. It's there. That link is in the PowerPoint. You guys can watch it over and over again. Okay. How are we doing? Questions before I keep moving? Is everyone having fun? It's not Monday, it's Wednesday. You guys can't look sad. It feels like Monday. Who enjoyed that extra little vacation? Boy, did I enjoy it. Yep. I mopped my floor. It was good. This is where life is going, guys. You're like, I feel so good. I did laundry and I mopped my floor. Oh. Okay. Microtubules. Okay, so with microtubules, growth and shrinkage is dependent upon the presence of a GTP cap. What is a GTP cap? Is it a cap made out of GTP? No, it's actually a cap of GTP bound subunits. Okay, remember you've got your alpha beta heterodimer, tubulin heterodimer, and it's being added and added and added, right? And what happens? So if this is your GTP cap, and as you have your GTP cap, you're more likely to add more monomer and grow. But what happens is that GTP hydrolysis is a little slow, and that's what allows this cap to develop. So you're adding. GTP hasn't hydrolyzed yet, so you've got this GTP cap. So growth. And then what happens, you start to get hydrolysis. Nothing other than just the normal rate of GTP hydrolysis by the tubulin monomers. And eventually it catches up and you lose your GTP cap, and that's called catastrophe. I love it. Who loves that? When I learned this in grad school, I didn't learn this till grad school, by the way. I think my cell biology professor was like, I hate the cytoskeleton. I'm not talking about it. And I always remember them talking about catastrophe because it's so dramatic, right? Anyway, so that results in catastrophe, which is rapid shrinkage. So once you lose your GTP cap, everything starts to dissociate. Because remember, GTP-bound monomers want to bind, but GDP-bound monomers want to dissociate. So if you lost your GTP cap, you're going to have rapid shrinkage, which is why it's called catastrophe. And then you can have rescue, which is where you start to regain your GTP cap and start growing again. And that's what accounts for dynamic instability. It all has to do with GTP hydrolysis and the presence of the GTP cap. Okay, questions, comments? Okay. I think I might have another movie coming up with that. I'm not sure. Okay, so another way to think about dynamic instability. Here's your microtubules. Here's your GTP cap, right? So these are all GTP bound. The GTP hydrolysis has not happened yet. You're having growth. And then eventually the GTP does hydrolyze to GDP, and then you start to get the shrinking. So the GTP cap is keeping microtubules growing. And when the cap is lost through GTP hydrolysis, depolymerization is likely to occur, which is called catastrophe. Okay, I think I got some movies here for you. Let's see. All right, so that's the one we saw the other day. And so here's your centrosome, and this is where your microtubules are organized in a cell. If you notice, your microtubules, when it's interphase, are all in the center, like they're all radiating out of the center of the cell. And that's what you're seeing is that growth and shrinkage is every time it's backing up. Let's try again. Oh, come on. Every time you see it growing, you can make the assumption that it has a GTP bound cap. And every time you see it shrinking, you can make the assumption that you're having hydrolysis. Let me turn off the light. You see those that growth and shrinkage? That all has to do with GTP hydrolysis. Do we want to watch it once more? You feel good? Yes.
So is the MTOC in the centrosome or at the end?
It is. It basically is the centrosome. So we're going to go through the anatomy of the centrosome, and it is. It's the microtubule organizing complex, which contains gamma tubulin something complex, where it's and that nucleates the microtubules. Okay. Once more, just for fun, for those who love movies. Right, so GT by hydrolysis, GTP cap, GT by hydrolysis, over and over again. Okay, so I will leave the light off in case it will help for the next one. So that's actually GFP labeled microtubules, and you could see them growing and shrinking, right? Very cool, huh? All has to do with GTP state. Okay, so I think that's it for right now.